All right, so we are going to be looking at section 6.1, estimating with finite sums. We are beginning the new section of calculus dealing with what are called integrals. So this is kind of our first little introduction to that. Here's our picture that we have here. I don't know if anybody's ever been to Greenfield Village in Michigan, but it's really a cool place to go. I've been there. So consider an object moving at a constant rate of 3 feet per second. We know that distance is rate times time, or we could say rate times time equals distance. So then the 3 feet per second represents the rate. So we know that 3 times t equals d. If we were to draw a graph of the velocity, the distance that the object travels is equal to the area under the line. So we know that if this is our velocity, and our velocity is measured in feet per second, and our time is measured in seconds, then we know that if we are going to multiply, or we know that we can, 3 feet per second times 4 seconds equals 12 feet. So the units just kind of work out. If with this velocity graph, we know that if we multiply the 3 feet per second, because that's a constant, so we have a constant velocity, 3 feet per second, and if you travel at 3 feet per second for 4 seconds, then you guys know to multiply 3 times 4. So we can think of this as the area under the velocity curve. So the velocity, which happens to be a constant, so it's a horizontal line, we can think of that as our velocity function. And then the area that's represented under that curve represents the distance that the object has traveled. So if the velocity is not constant, we might guess that the distance traveled is still equal to that area under the curve, and that would be correct. So for example, because the units would work out. So suppose now we have a function that is not, it's a quadratic. So we have the velocity is 1/8 t squared plus 1. And so clearly not a constant. So if we wanted to find the area under the curve, we don't have a formula to find this area under the curve like we do if it was a rectangle. So what we can do though is we can actually estimate the area under the curve by drawing rectangles that touch at their left corners. So for example, and this actually has a name, the left-hand rectangular approximation method, or LRAM for short. So if we were to start making a table of values, and we're going to use the left endpoints, which means that we're going to start with a 0. So if you plug in a 0 into the function, you get 1 for the velocity, and then that represents the height. So the height of that rectangle would be a height of 1. The velocity is our height when we plug those in, and we see that we get an area of 1. That rectangle has an area of 1. If we let t equals 1, so that's again the left endpoint, you plug that in and you get 1 1/8. So that's the height of that rectangle. So the area would be 1 times 1 1/8, so we get an area of 1 1/8 of that rectangle. Next you plug in a 2, and when you do, you get 1 1/2. So there's that rectangle. And then you plug in a 3, that would be your last left endpoint, and when you do, you get 2 1/8. Now, if you add those together, you get 5.75. So that represents our approximation. Now clearly this is going to be an underestimate because notice the white space up here. So we have this extra additional white space. So clearly we have an underestimate for the area using LRAM. We could also do the same problem with the right-hand rectangular approximation method, RRAM for short. This time I'm not going to use the 0, I'm going to use the 1 instead. So if you plug a 1 into the function, they didn't do a table of values there, but because we already did those. But if you plug a 1 into the function and then plug a 2 in, plug a 3 in, and plug a 4 in, and get the appropriate areas, and when you add up all those areas, you get 7.75. Now this clearly is going to be an overestimate, because all of the rectangles go above the curve. We're trying to approximate the area under the curve. So this one clearly would be an overestimate. So another approach would be to use the midpoints of each section called MRAM for the midpoints. So then that means instead of using a 0 or a 1, you would use a 0.5 because you would use the midpoint. So 0.5, and if you plug 0.5 into the velocity function, you get the height. Do the same thing with 1.5, and then with 2.5, and then with 3.5. So you can see plugging those in, and you can kind of tell just looking at the picture, this is better because you've got white space here, you know, it's overestimate on this part, under. It's not going to be perfect because this piece is not exactly the same size as this piece. So it's not going to be exactly correct, but it's better. The MRAM is going to be better than LRAM and better than RRAM, most definitely. So we can see a better approximation. When you combine those, you get 6.625. If you were to check an average LRAM and RRAM, it's not the same as MRAM. So you can verify that if you want to, but it's not the same. So we have 4 intervals in the example we just did. If you want a better estimate, then you just need more rectangles. So if I increase my number of subintervals, my accuracy is going to get better. I'm going to have less white space if I'm under the curve, less of this above the curve. So here is if you do MRAM with 8 subintervals, that's what this example is. So instead of 0.5, I'm going to use 0.25 now because we're going to use more intervals. So if you use 0.25 and plug it in and do similar with all the rest of them. So this was 0.25, this was 0.75, this is 1.25. I'm just pointing to the midpoint parts. When you do that and then add up all those areas, now those represent all the heights of the rectangles. Well, to find the area, you multiply the height times the width of the rectangle. So you actually have to multiply by 0.5 because the width of the rectangle is 0.5. So then you have to do the height times the width. These are all just the heights. So you add them all up and then multiply by the width of the subinterval. When you do that, we get we get this answer. That's the approximate area under the curve. And we're getting closer to the actual area, which we'll learn how to do later when we have functions. The exact answer for this problem would be 6.6 repeating. Just a little definition, inscribed rectangles, what that means is the rectangles are all below the curve. So if it's inscribed, they're all below the curve. If it is circumscribed, that means they're all above the curve. Now, for this particular example, the inscribed is left endpoint. Notice that the left endpoint determines the height of the function, and the circumscribed, it was the right endpoint determined the height of the function. Do not assume that's always the case. This particular function is concave down. If the function was concave up, then we would see that reversed. So, but just a little definition on what is meant by inscribed and circumscribed. We will be learning how to find the exact area under a curve if we have the equation for the circle. We're going to do that a different way. We're not going to use RRAM and MRAM or LRAM. We're not going to use all of those with rectangles. If we know the function, then we have a way to get the answer exactly, so we don't need to do approximations. However, sometimes you're not given a function, you're just given data, and you have to come up with an approximation. And so that's what we're going to look at now. I have an example for us to do similar to that. So this problem is number 16 from your textbook on page 275. So we have the velocity of a model train engine moving along a track for 10 seconds. And we are being asked to estimate that distance traveled by the engine in during that 10 seconds using 10 subintervals of length 1. And first we're asked to do it using left endpoint values and then with right endpoint values. So just to kind of see what's going on, when the train starts at 0 seconds, it's going 0 inches per second. 1 second later, it is now going at 12 inches per second. at time equals 2 seconds, another second later, it's now going at 22 inches per second. Then it slows down to only 10 inches per second. So this is telling us the velocity. So what I would recommend doing to kind of get an idea of what's happening, remember that the distance traveled is the area under the curve. So I do a graph of that. And what I did was I put my time on my x-axis, my velocity on my y-axis, scaled that, and then I'm going to kind of just plot some points to get an idea of what's happening. So we have 0, 0, 112, 222, 310, 4, 5, 5, 13, 6, 11, 7, 6, 8, 2, 9, 6, and 10, 0. All right, now I'm not going to connect the dots because what I'm doing is I'm going to be doing either left. I'm going to start by doing left endpoint values. So we're going to be making rectangles using the left endpoints. Before I do that, whoops, let me clone this so that when I do the right endpoints, I can just use that next picture. So the very first one, using the left endpoints, is a height of 0. That would be my first rectangle. Yeah, not too interesting. My second one, using the left endpoint, would be this. So here would be my second rectangle. My third one would be using this. And then the next one would be here. The next one would be here. The next one here. I should have used a different color. And then here. And here. And here. Oh, one more. And here. Now notice how this last one doesn't have one. And even if it did, it would just be another 0, 1 down there. But these would be the rectangles using the left endpoints to build my rectangles. So then I would be, I need to add up all the heights and then multiply by the width of the rectangle. Or if you prefer, you could do, now these are all a width of 1, so that makes life a little easy. But sometimes they're not. So you could do length times width plus length times width plus length times width plus length times width and do that. But since they're all the same width, you can just add all the lengths together and then multiply by the width. So notice that when I add all the lengths together, if I'm doing LRAM and using my left endpoints, then I'm going to use these for my velocities, for my heights. I'm not going to use the last one. Now in this particular case, it happened to be a 0 on both ends, so this is probably not the greatest of examples because my LRAM and my RRAM, I'm going to end up using the same values. So, but what I would do is then I would add 0 plus 12 plus 22 plus 10 plus ... plus 6. And that would be the sum of my heights times the width of the interval, which in this case is 1, but keep in mind it's not always. And then that would give me my answer for the approximate distance. So if you do that, you end up with 87 inches, and that would be the approximate distance because that would be the area under the curve using rectangles. Again, if I actually had a function that I could use, we are going to learn a different method. This is only if this method is still applicable for us, though, if we actually have data. So that's where this is important for us. Now, to do RRAM, I'm just going to use this on here. It's just going to be using the right endpoints instead. So I won't have this. Instead, I would have this as my last one. So using right endpoints, the 1 and then the 2 and then the 3, so I wouldn't use the 0. So it would be these instead. Like I said, this one is going to be the same because the two endpoint ones, the two last ones were 0, so it didn't make any difference whether I was using the LRAM or RRAM. But that won't always be the case, and on some of the homework problems, I know it won't be that way. So again, that would indicate that the train traveled a total distance in that 10 seconds. It traveled a total distance of 87 inches.